Okay, so let's calculate the pH of a weak acid. So remember, we've got to use that Ka expression. We can't use the assumptions like we did for a strong acid. Okay, so we use that Ka expression. So here's the question. So calculate the pH of 0.03 moles per dm cubed of ethanoic acid at 298 Kelvin. The Ka for ethanoic acid at 298 Kelvin is 1.76 times by 10 to the minus 5 moles per dm cubed. So first of all, what we're going to do is write down our Ka expression. So Ka equals H plus squared over CH3COH, which is your ethanoic acid. So the second thing is we rearrange to calculate the H plus squared. That's what we want to work out. Because remember, to calculate pH, we need to know the H plus concentration. So H plus squared equals Ka multiplied by the concentration of ethanoic acid. So H plus squared is 1.76 times by 10 to the minus 5 times by 0.0300. That gives us a H plus squared of 5.28 times by 10 to the minus 7. So that's the concentration of acid ions squared. So that's the key thing. Because it's squared, we've got to take the square root of that answer to get just H plus, because that's all we want. So we take the square root of that answer and we get 7.27 times by 10 to the minus 4 moles per dm cubed. That's the concentration of H plus ions that this acid has produced. But we need to work out pH. So to calculate the pH, we put it into that formula. pH equals minus log of H plus ions. That's what we've just worked out. So minus log of 7.27 gives times 10 to the minus 4 gives a pH of 3.14. Again, look at the number. Is that sensible? Yes, it is, because it's a weak acid, so therefore our pH has got to be 3.14. It's still the same. Okay, so let's use that Ka expression, but this time what we're going to do is we're going to calculate Ka, or the concentration of a weak acid. So instead of working out pH, we're going to work out something else. So here's another example. So we're going to calculate the concentration in moles per dm cubed of methanoic acid, HCOOH, at 298 Kelvin with a pH of 3.14. The Ka for methanoic acid at 298 Kelvin is 1.77 times by 10 to the minus 4 moles per dm cubed. Wow, there's a lot of information there. Right, so let's start. First one, calculate H plus. So the concentration of H plus in the pH equation. That's what we've got to do first. So the pH is minus log H plus, and we rearrange that to give us H plus equals 10 to the minus pH. So we've got to work out the H plus first. So remember, we looked at the previous slide. Use your calculator, shift, log, you get your 10, your flashing box, just above the 10, you put in minus your pH, which we know is 3.14 because we've been told that. So therefore, the concentration of H plus ions here is 7.24 times by 10 to the minus 4 moles per decimeters cubed. Okay, so then we write down the Ka expression. So Ka equals H plus squared divided by methanoic acid. Then we rearrange that to calculate the concentration of the acid, because that's what we want to know. So that's H plus squared over Ka. We know what H plus is because we've just worked that out there. So we do 7.24 times by 10 to the minus 4 squared divided by Ka, which we've been told. So that's 1.77. And so the concentration of weak acid is 2.96 times by 10 to the minus 3. So calculating Ka is exactly the same. We just repeat steps 1 and 2, but we just substitute the numbers into this straight away. We don't actually even need to rearrange. So we just do H plus and divide it by the concentration of the acid, which in this example you would be given if you're asked to work out Ka. So it's that's even more straightforward. So you can see all we're doing is we're using a lot of these equations and just pooling them up. So have them equations in your mind and try and think, right, which one do I need to use? And some of them, for example, contain H plus. pH contains H plus, Kw contains H plus, and Ka contains H plus. So there's a lot of equations to contain H plus. So a good idea is, if in doubt, calculate H plus, because the likelihood is you're going to be able to put it in some form of equation if you're unsure. Okay, so this one's a new one. This is called pKa, or calculating it. So pK is another way of measuring the strength of an acid, similar to pH, And you'll notice there's a little bit of a similarity. They both start with a little p. So the lower the value, the stronger the acid. Again, just like pH, the lower the value, the stronger the acid. So pKa is the minus log of Ka. Now that rings a bell because pH is the minus log of H+. So in theory, you could say that the P bit stands for minus log of something. So that's how you can remember it. So pKa is the minus log of Ka, pH is the minus log of H+. See? So there is logic behind it, you see. So calculate the value of pKa value of an acid with a Ka value of 7.52 times 10 to the minus 3. This is dead easy. We just do minus log of Ka, and this gives us a pK of 2.12. So remember, the lower the value, the more acidic it is. We can also rearrange that, so we can do Ka equals 10 to the minus pK. Again, that's the same thing, shift log on your calculator, and we put minus pKa in. So for example, calculate the pH of 0.0250 moles per dm cubed of ethanoic acid at 298 Kelvin and has a pKa value of 4.75 at 298 Kelvin. So the first one, calculate the Ka first. That's the first thing we need to do. So Ka equals 10 to the minus pK. So 10 to the minus 4.75. So our Ka value is 1.78 times by 10 to the minus 5. It's fairly straightforward when you look at it. It's just there's a lot of things in there which think, crikey, that's quite scary. Unless of course you do A-level maths, of course, and that may make it a little bit more easier. So then what we've got to do is we've then got to calculate H plus from the Ka expression. So this is the second thing we need to do. So we know the value of Ka because we've just worked that out, and this is the Ka expression that we use here. So H plus squared, so we rearrange it to get H plus squared, which is Ka times by our ethanoic acid, which is effectively 1.78 times 10 to the minus 5, multiplied by 0.0250, because we've got that there. H plus squared is 4.45 times 10 to the minus 7, and then H plus, which is this bit here, concentration of H plus, is square root. So remember to square root it, because this is telling us about H plus squared. A lot of people miss that bit, and they end up just putting that as the answer and saying, oh, well, that's it. So be really careful. The final thing, now we know the concentration of H plus, we can then work out pH. So pH is minus log H plus. So pH in this example is 3.18. Again, check to make sure that's sensible. Don't just take the number as a for its own worth. This is ethanoic acid. It's a weak acid, so we'd expect weak acids to be around pH 3-4. So this looks about right. It's quite a strong weak acid, but it's still a weak acid nonetheless. Okay, so how do we actually measure the pH experimentally? Because a lot of this is about calculation and theory, etc. But at the end of the day, we've got to carry out things practically, and we've got to know how we can measure the pH of a substance to either work out the concentration of something or to use the formulas as we've suggested there. So what we do is we use pH meters, and pH meters, they measure the pH of a solution, but they've got to be calibrated. Now, if you've used one of these in the lab, you'll know what a nightmare they can be, and you've got to use buffer solutions, and we'll come on to buffers in a minute, that's another thing. But buffer solutions, and you basically calibrate it using that. So the buffer solution would have a buffer of 3, say 3, 7, and 9, let's say, and you'll put your pH meter in and just make sure it is reading what them chemicals are. So the pH probe must be placed in distilled water first. You've got to clean the end of it, and you've got to be careful. The end's quite delicate. The meter should be reading 7 if it's in pure water. So you've got to adjust that if it's not. Then what we do is repeat the process with standard solutions at pH 4 and pH 10, and make sure that you rinse it with distilled water between each pH solution. So in other words, make sure it's pH 7. If there's one of the testing one, this is tap water on it. But if this is in a buffer solution of pH 4, let's say, and we put the pH probe in and it comes out as 3, we need to adjust, we need to calibrate that because we know that that's 4. Okay, and you'll see in a minute why. pH meters, they should be calibrated for use because, it's a bit like getting on the scales. If the scales is already showing 2 stone, let's say, and you step on it, then you're going to be 2 stone heavier. the scales is going to say you're 2 stone heavier than what you actually are. So this is exactly the same, except this is for pH meter. Okay, and we always wash the probe after each test. So we do not just stick it into different substances, because you'll just contaminate it. You've got to wash the little end of the probe to make sure it's completely washed of contaminants.